Just one moment, we have some problem here with the projector. Prego? Sì, non è a tutto schermo, vedi, c'è solo io qui ce l'ho a tutto schermo. Sì, purtroppo. Ottimizzato. Proviamo così. Mi dispiace. Okay, so we left last time on this slide where we were discussing the variation of the critical temperature, Martensite finish, Martensite start, austenite start, and austenite finish for a shape memory alloys, variation by the stress variation. And we saw that there is essentially a linear variation for all the four temperatures, which allows to us to define, according to the angle alpha and beta, the slopes, which are written as Cm for the Martensites and Ca for the austenites. So we do have a linear variation of the critical temperature by increasing the stress. Thus, if we have in mind our general equation, which gives to us, for example, for the Martensite to austenite transformation, the percent of Martensite, which is still retained, we saw last time that it can be written, in this case, like C equal to C divided by 2, multiplied by a cosine of an angle plus 1, without this added term here, without, let me say, this added term, okay, which is now added, as you can see, it's a linear term, in order to take into account the variation of the critical Martensite temperatures. And we can define, in this case, the BA coefficient multiplying the stress, which is given by the ratio with minus before of alpha A, we already defined last time this term, divided by the slope CA. We can apply the same concept if we are going to look to the austenite to Martensite transformation. As you can see, also in this case, we can add this linear term, which takes into account the variation of the austenite's critical temperatures, with a coefficient written as Bm, which is given by the ratio of alpha m, we defined also alpha m last time, divided by the slope Cm. And so this is the general formulation for the martensite to austenite, or for the austenite to martensite transformation, in which we are going to take into account the possibility to start from an initial point where Xi is not equal to Xi0. So we have Xi0. Sorry, the initial point where Xi is not equal to 0, but we have a percent of martensite of austenite at the beginning, and we define Xi0, the percent of martensite originally present. So it's a general formulation. Then we have the effect, which is given by variation of temperatures. That is, we have this term that is the real temperature here and here also. And then we have added also the stress effect. That is the variation of the critical temperatures when we apply a stress with the two linear terms, which are dA multiplied by the stress, or dm multiplied by the stress for the first case transformation and for the second case transformation. And this is the general formulation which can be used and which is allowed, which allows to us to model the possibility to have shape memory behavior caused by variation in temperature, and the possibility also to have shape memory behavior which is related to variation of stress applied. So with this one, we can describe the shape memory behavior also in the case in which we have superelasticity or pseudo-elasticity of the material itself. And for example, if we have the martensite to austenite transformation, and so we have the general equation, which is this one, the first one, martensite to austenite transformation, and we are working at a fixed temperature values, that is T is a fixed value, not varying in this case. And then we are, because we already have said that, a temperature which is in the range between MD and austenite finish AF temperature, we can have a variation, as you can see, of the angle theta, which is defined in this way completely, even though we keep the temperature here constant, but we apply a stress which is variable. And we can make the same approach that we have used for purely thermally induced shape memory behavior. That is, this value of the angle theta, which is the argument of the cosine function, can vary between the two extremes, 0 and pi greco. And so we can define which is the upper limit and the lower limit in terms of stress for a constant temperature value between MD and AF in order to have stress-induced martensite. So we can put 0 to get the first limit, we can put pi greco to have the second limit, and so we can calculate, as you see, the upper limit of stress, which, when it is applied, gives to us the complete transformation of martensite to austenite, and the lower limit of stress for which the transformation is going to start. This is during the MA transformation, but the same approach can be used if we are looking to the austenite to martensite transformation. I mean, also in this case, we can define by using the two extremes, 0 and pi Greco, but with a proper formula, that is with this formula here, we can define the lower stress, this one, for which the austenite only by stress, but a constant temperature value, is starting to be transformed in martensite, and the upper limit of stress, this one, for which the austenite is completely transformed at constant value of temperature to martensite, that is Xi equal to 1. So we are able to model with this general formulation both the transformation martensite to austenite and vice versa given by pure thermal effects and transformation of martensite to austenite and vice versa, which are instead stress induced, that is, they can happen at a constant temperature value. Remember again, this constant temperature value is in the range austenite finish and temperature, characteristic temperature MD of the materials. Thus, looking to, let me say, a general stress-strain behavior, if we are going to discuss the stress-induced martensite, this means that we can define, let me say, a sort of linear, elastic linear stress, limit stress, for which there is no transformation of austenite to martensite, for example, during the loading phase, because we have not yet reached the lower limit to get transformation. So we do have an initial behavior of the shape memory alloy, which is essentially purely elastic. Then when we reach the lower limit for the austenite to martensite transformation, the phase transformation starts. We do have deformation, and that deformation are those which are linked to the shape memory behavior. We must not exceed the upper limit of stress because we would enter in a range of deformation during the unloading phase of the materials itself. And this is what we have discussed at superelasticity. There are many materials, not only shape memory alloys, metallic alloys, which can show this kind of behavior. You see, for example, this is hairs in the head. This is the classical behavior, which we will discuss a little bit further on, of annealing alloys. This is the behavior of bones. And you see, we do have a linear part, which is an elastic linear part. Then around here, it is located the lower limit of stress to have austenite to be transformed in martensite. This here is can be the maximum limit, upper limit stress to have all the austenite transformed in martensite only by stress. And then we do have the unloading part of the curve where we can identify, for example, here, or for example here, the initial stress values in which martensite is going to be transformed again in austenite, and here where all the martensite is transformed in all the martensite is transformed in austenite, that is C becomes 0. In some cases, you see, we can recover here the deformation because this is a sigma epsilon. Stress strain really it's a force, but we can identify it as a stress strain diagram. We can recover the stresses. Sometimes, like in this graph, there is a stress which can be of some 1.5%, which is not recovered. It can be present or not. In the case it is present, this is a non-recoverable strain, and we say that the shape memory alloy has a sort of amnesty, does not recovering all the imposed stress during the transformation phases, which is again around a maximum value of 10%, like those we have already said for behavior purely related to temperature changes. Have a look to this one. This one is a realistic diagram for N-ethanol, nickel titanium, the shape memory alloys, which is interesting for us, in the case of superelasticity. That is, we are, as you can see here, at a fixed temperature value, which is in the range, as we said, MDAF, and then we have the transformation of the phases by applying a stress, and this is a superelasticity, at this constant temperature value. Linear part, then here we have the stress, the lower limit of stress for austenite to martensite transformation. This is the upper limit of stress in order to have all the austenite transformed in martensite. More or less here we have the stress, which is the stress for which the martensite start to be transformed again in austenite. And here you have the stress for which all the martensite is transformed to austenite, that is C equal to 0. You see here 0.5% more or less of amnesty, that is of non-recovered deformation. If we have a look to this diagram, we can discover a very interesting things. You can see that during the unloading, there is a quite relevant part of the diagram for which the stress given back is more or less constant, a sort of plateau during the unloading part of this diagram. And if we have a look also to the figures, if we have a look also to the numbers, we can say that as lower limit, this constant stress, which is given back by our materials being transformed from the martensite phase to the austenite phase, is at minimum 150 megapascal, MPa. So this is very interesting because if you remember 150 megapascal, they are 150 Newton per square millimeter. So this means that they are 15, that is 1.5, kilogram, I mean kilogram force, per square millimeter. So this means that, for example, if we have a wire having a cross section of 1 square millimeter, it gives back to us a force able to move 15 kilograms. So it's quite a significant number, and this has suggested the possibility to use this superelasticity effect in order to move a mass, in order to have a sort of linear actuator. And this is another field of potential application for the shape memory alloys, but we need to keep in mind one limitation. Because of, if we want to have, let me say, more performing linear actuators, which belongs to the class of smart materials, we need, and we will do it, to refer to another class, the class of piezoelectric materials, which is the main limitation. The main limitation of this behavior is in terms of cycling behavior, that is frequency. So the answer in these terms of the shape memory alloy is not very fast, and it can be used for cycling movement just if we have some few hertz of frequencies to be satisfied. If we are thinking to fast actuating movements, we need to change the materials from the nitinol shape memory to the piezoelectric materials, which we will discuss in another lecture. So this is just to resume to you shape memory effect, which can be, as we said, driven by temperature change or by stress at constant temperature. And this we already said last time we discussed. There are some characteristic temperatures for nitinols, and we told, just to recall to you, that the critical temperature can be varied for the same alloy composition according to post-processing treatments of the alloy itself. And thus, we can have values that are defined, generally speaking, as low temperature values, identifying the Martensite finish temperature, which are not so low, in the order, for example, of room temperature, as well as we can have high temperature values, which are usually identified with the austenite finish temperature, which are not so high, again, depending on the alloy and on the treatment. They can be also some tens of degrees, not high temperature like those we have or we can meet inside a combustion chamber of an aeronautical aerospace engines. So they can be tailored according to the needs of the potential applications. One interesting application that I want to mention to you for what it concerns the use of shape memory alloys is coupling for pipes. I mean, we do have two pipes, this one and this one, that we want to couple without, for example, any welding. One thing that we could think to do is to put a sort of ring, this one, which is able to fix the extremes of the two pipes. Obviously, in order to have joint like this one, effective joint, this ring that we insert must compress a bit the surfaces of the two extremes of the pipes. Otherwise, it will move along the length of both the pipes. And so what does it mean? It means that the inner diameter of this ring, this one, should be a little bit lower in terms of value of the outer diameter of pipes 1 and outer diameter of pipes 2. But if this is the situation, in order to have coupling, we are not able, since the inner diameter of the ring must be lower than the outer diameter of the pipe, we are not able to insert the ring along the pipes. But we can think to use a shape memory alloys, which with procedures. Well, conceptually is very simple in the sense that this final configuration where the inner diameter of the ring is lower than the outer diameter of the pipes must be for us the high temperature configuration, that is the initial shape and size, if you want, that we have to recover after having activated the shape memory alloys. So we start in the austenite phase with this configuration of the materials. Then we can, for example, by varying temperature, allow the transformation in this ring of the existing austenite to martensite, 100% martensite. And the temperature that we need to reach depends on these characteristic temperatures. Okay, so you can see, for example, we can do this one also at room temperature. For example, when we have all martensite, we can more easily deform the martensite. So we deform the ring in the way that its internal diameter now is a little bit higher in terms of value of the outer diameter of the pipes. So we can insert the ring between the two extremes of the two pipes. Then we activate the shape memory alloy behavior, for example, heating, because remember that when we have by temperature to transform austenite to martensite, we need to cool. Then when we want to recover the original shape and size, which was fixed at austenite phase, we need to heat. So we heat. By heating, and we are now able to model, let me say, the heating and the cooling phase also with the general equation we have seen before. By heating, we have the transformation of the martensite to austenite. The impressed strains, that is the impressed deformation, are recovered, and then we can achieve our final solution with this ring, which is placed in position, which couples well the two pipes, because the inner diameter after recovering the austenite phase is lower in value than the outer diameter of the two pipes to be jointed. We can also define, according to the final inner diameter of the ring, how much is the compressive stress. We can calculate that, and so we are in the condition to design a treatment and a solution, in this case for coupling without any welding. And this has been used, for example, in the so-called cryofit hydraulic pipe coupling in the F-14 jet fighters. So they are not, let me say, very commercial application. And you see here the insert that in that case have been used, made by Nitinol, by shape memory alloys, exactly with the same principle we have qualitatively discussed here. Other application of shape memory alloys, which have been tested, proven, and which are existing, and in the special case of Nitinol, again, as I told to you, this is the alloy which is interesting for us, is the use, for example, in release of bolts. And these shape memory bolts were developed and used to replace conventional exploding bolt devices in aerospace release mechanisms. Also in this case, for example, if we give head, for example, by giving head, we can have induced stresses inside the materials, because, for example, it's going to recover the original form. And then we can have the possibility to break the materials and to release the bolts, as well as I told to you, self-erectable antenna, space system vibrational damper also, and then some application in Mars Sojourner rover actuator. Also in some, let me say, very special application like this one, you can see it, you can recognize, which is not a commercial airplane for passengers, but it has another target. Knitting of wires have been used for actuation systems. As well, they can be used, not in the commercial way, in order to have to match the so-called smart airplane wings, that is modifying shape and size, or by using, for example, smart shape memory alloys wires, by giving temperature. And then I will say to you one thing, because this is in principle quite simple. We can, for example, modify the geometry of the wings in order to have intelligent or adaptive wings profiles. In this case, as well as, for example, in this case for actuators, or in the other one that we have mentioned, also in the release bolts, we need to move temperature to different values. So it's quite difficult to think that we can have temperature variations by putting the wing or by putting the bolts inside a furnace. That cannot be made. But please do not forget that we are talking about metallic materials. And one possibility to heat, for example, metallic materials is, in addition to the possibility to use a furnace, is to let current intensity to flow inside the materials. And this is quite simple and also easily described if you think, for example, to wires, because we have the Joule effect. So we have a variation in temperature. Then depending on the cooling way adopted, which can be a forced cooling or a natural cooling, we can have also the cooling phase. And so we can have the thermal cycle, which can activate for an N-way, not one way, N-way shape memory alloys, a cyclic behavior which responds to the needs, to the design needs. So by using a current density, by let current to flow inside the wires, we can easily define and vary temperature, and we are also able to model it. We will see one example later on, without using a furnace. Okay, these are some, just for the purpose of your curiosity, some other applications in which memory alloys have been used, the so-called SMA butterfly. Again, in this case, the wings of the butterfly can be moved by inducing shape and size change by using wires of nickel titanium in which current density is going to flow inside in order to move the temperature. Linear actuators, as we already said, but also other applications which are outside our fields, because in the biological fields, shape memory alloys are quite extensively used. For example, in bond plates, for example, in surgical anchor, for example, in cloth filter, etc., as well as eyeglasses that we have already mentioned. Here are some example of just picture, orthodontic, as we told before. Now we will say a little detail, and other applications which are referred to bones, generally speaking. This case, the case of orthodontic application of shape memory alloys knitting of wires, is going to work by using essentially the superelastic effect of the shape memory alloys, which is the aim. The aim is to make the fit right, okay? To get the right alignment between the teeth. So we are going to start from a disaligned situation. And so we need a force in order to force the teeth to achieve the right direction. And this force is what is given, I go back, during the unloading part of the car, which is, for this kind of material, for a certain period of time, till we recover all the deformations, is something which is constant. So the effect is really present and is an effect not variable, because the stress which is given back by the materials during the unloading phase is constant. But in order to have, in order to have here a constant stress, we need before to load the materials, because during the loading phase we have the austenite to martensite transformation at a constant temperature, which is the temperature inside our mouth, okay? And during the unloading phase, the materials give us back a constant stress. How we can load? We load with this small spring. If somebody of you have seen with small, there are in some cases there are springs which can be moved by your hand. You are asked by your dentistry to move this spring for some minutes every 2 weeks, for example. During the movement of springs, we are loading the wire, okay? So we are loaded, then during the unloading phase, we have a constant stress. This effect is going to be present for a couple of weeks, more or less 10 days, 14 days. Then we have to unload again, and then we have again the unloading part of the hole, and so on, in order to use this positive effect of the superelastic behavior. These other pictures, just for your curiosity. Now, this is the example instead of the optical frames, eyeglass superelastic here, which we discussed qualitatively last time, and in which, again, also in this situation, being the system essentially at room temperature, that is a constant temperature, the shape and size recovery after also accidental deformation of the eyeglass frames is given back by the superelastic effect of the materials, apart from that very small percent of amnesty which can be present. Now, we talk about actuators, okay? And the possibility to actuate a movement, that is to move a weight, for example, to move a mass by using the shape memory alloy behavior. Let's see it as how, for example, an helical springs can be designed if we think that this springs is made, for example, by a nitinol alloy, or generally speaking, by a shape memory alloys. Again, we are talking about the possibility to have this effect not only one time, but many times. So we are speaking about end-way shape memory alloy behavior. So what do we need if we want to go on with the design, with this conceptual design? First of all, we need a shape memory material. Okay, That's a fact, okay? And we define it as an ethanol. Then we need the possibility to define how modify inside the shape memory materials the percent of austenite and the percent of martensite. We are using a wire. Since we are using a wire, we think that we are going to induce this shape memory behavior by varying temperature. And so we need a thermal model which is able to say to us for a given temperature, which is the percent of austenite and which is the percent of martensite. We need thus something which is before this thermal model, which is the point B, what we have discussed, the phase transformation model, because we need to condition the temperature value. And so we need a thermal model in the sense that, for example, applying a current density, a current intensity, we must be able to say after what time that value of temperature has been reached, okay? And then we need something which is able, that is a mechanical model, to link the phase transformation model with the force, with the stress, which can be given by the shape memory materials when the shape memory behavior is activated. These are three blocks, okay? And so let's see these three blocks a little bit inside. First of all, the thermal model, the pure thermal model. The pure thermal model is quite simple because what we can say that if we are going to study temperature variation with time through the classical, let me say, thermal balance, we can say that the mass density of the materials multiplied by the specific head capacity of the materials multiplied by the volume of the materials multiplied by the variation of temperature with time must be equal to the head which is generated by an external source, for example, through current intensity, but we will link this later on, which must be lowered by the losses, which are in general losses due to conduction, due to convection, and due to radiation. Well, if we are going to put our attention on the first term, that is the head generated by an external source in terms of power, you see here that if we are going to use current intensity, this terms is very simple because it's just the Joule effect. So you must multiply the electrical resistance of the wire, in this case, by the square of the current intensity. So I square multiplied by R. And this is the terms QS. Then, if we are going to discuss a little bit these three terms of losses, well, perhaps you remember that the radiation losses, they are dependent on the temperature with an exponent 4. And they are very active when the temperatures are very high. Now, if we are thinking about temperature which are in the range of 30, 40, also 100 Celsius, these terms essentially can be neglected if you want. As well as the losses by conduction also, in this case, could be neglected because we are thinking, we are discussing, even though they have shape memory behavior but noise. And so conduction losses are very, very low due to the fact that the thermal conductivity of the materials, of the metallic alloys, is relatively high. And so the most important terms for what it concerns the evaluation of the term, is not this, the conduction, is not this, the radiation, but is essentially the losses by convection. And so the convention can be written as, you can remember by your full examination, as the multiplication, the results of the multiplication of the heat transfer coefficient per the surface area through which convection is going to occur, and then the last term is the difference in temperature. So our general equations in terms of thermal balance is at the fourth stage quite simple, because becomes this one where we have the given power and where we have the losses for convection. So in this case, we need to solve this equation. If we solve this equation, I mean, for example, giving a value of the current intensity, fixing the value of the current intensity, if we solve this equation, we are able to answer after to the question, which is the temperature after 1 hour, 2 hours, 3 hours, 1 millisecond, 2 milliseconds. So we are able to define temperature variation with time for a given current intensity flowing inside our wire. These are the generic, just to recall to you, let me say, parameters for helical springs. So we have a number of coils. We have the outer diameter. We have the diameter of the wire. All parameters that are needed later on, the geometrical parameter, in order to completely, let me say, treat the problem that we have defined now. When we solve that equation, so we have these solutions, and we have a solutions on heating, we have a solution on cooling. What I mean? I mean that when we are going to heat, you see here, we have the current intensity. And so we are able, with the meaning of the parameters that are written here, that is, A is the thermal time constant and T0 is the initial temperatures of the shear memory alloys, in this case at the beginning of the cooling process. We are able to model the temperature variation with time during the heating phase and during the cooling phase. During the cooling phase, obviously, this term is put equal to 0. We do not have Joule effect. We have just losses for convection, and so decrease of the temperature of the materials. And so we know, by solving this, let me say, simple differential equation, how to graph the temperature variation with time, provided that we know the properties of the materials. One example for this needle alloy, which is called Flexinol 200, is reported here. In this case, diameter of the wire, diameter of the springs are design parameter of the springs. If you see here, resistivity is a property of the materials. AF, AS, MS, MF are property of the materials. And then you can also, let me say, study the cooling phase in the case in which, for example, we are going to make an hypothesis that free convection is the cooling mechanism. And so you have a specific value in air, H in this case, or if you want, in the case in which you are going to suppose that forced convection, so that a more efficient cooling phenomena is going to happen, and also in this case, the relative H coefficient, which is put here, you see, inside the thermal time constant A, is used. Specific head and density are also properties of the materials, and these are the properties of flexing on through hundreds. And so we can define these diagrams. So we can make, for example, for a fixed value of current intensity, you see the A picture with 300 milliamperes, we can plot the temperature variation according, for example, to time, obviously, and to diameter of the wire, okay? Or you can use as parameter not the diameter of the wire, but for a fixed diameter, the amount of current intensity. This is up to you. And we can model the heating phase and the cooling phase of the materials. If we want to have some linear actuation more than one time, well, we usually cannot rely on free convection because the temperature, the variation, the temperature decreases too slow with time. And so usually, as you can see here, we can use a forced conventions, and if we use a forced convention, no problems. We need to use here the corresponding H coefficient, but we can achieve a sort of temperature variation with time, which is very, very near equal to a sort of real thermal cycle. You see here, where you have heating, then you have cooling, then you have heating, then you have cooling. So you have on heating the Martensite to austenite transformation. On cooling, you have the austenite to Martensite transformation. You need to arrange the extreme temperature values in order, obviously, to match with the critical austenites and critical Martensite temperature of the material itself, because you need to activate the solid state phase change. So this is the thermal model, okay? And the phase transformation model. Nothing, you see here, different of what we have already seen in our general modeling, apart from the fact that here the percent of Martensite is not written with the Greek letter Xi, like in our previous model, but is written with the Greek letter Eta. But the other are essentially the same. You see here, we have the case in which temperature is higher than Martensite start. So, which is the percent of Martensite when the temperature is higher than the Martensite start? 0. The other case, when the temperature is lower than the Martensite finish, which is the percent of the Martensite? 100, that is 1. And when the temperature is in the range Martensite start, Martensite finish, which is the percent of the Martensite, that one which is given to us by the cosine function that we have already seen. You can observe here that we are not using in this model, because we are thinking about a phase transformation model which is activated by varying temperature, we are not using the linear term which takes into account the contribution of stress for the variation of the critical values of the critical temperature values, Martensite and austenite. So it is the first simplified form, for which we are also making the hypothesis that at the beginning the materials is 100% martensite or 100% austenite, depends on which way you are going to move. That is C0 that we have used in our general formula is equal to 0. So this is the simple, let me say, modeling we can do. And this is the phase transformation model. So having said that, we could discuss before going on another topic that is related to the fact, generally speaking, that when we have a phase transformation, and we have it inside this example, we have also a latent heat of transformation. So now we have never considered this, but if we want to be more precise, you see here that in our energy balance, that is the thermal model that we have defined at the beginning, which was essentially related in our fourth expression to this part, we can also, or we should also, we must also, then we can decide that this is not relevant, but if we want to be, numerically speaking, if we want to be precise, we need to include also the latent heat of transformation of martensite to austenite and austenite to martensite, which is obviously related to the variation with time of the percent of martensite which is going to be formed or which is going to be transformed. If we use this general formulation for the fourth term of our equation, I mean this equation here that we have written, okay, as at the beginning, now we have just modified this equation by using the latent heat of transformations, the second term still remains the same, obviously. Then, for purpose of your curiosity, here you have the solution of this problem by using a dimensionless approach proposed by these two scientists. Let's go to the result. This is the approach for the dimensionless solution of the equation. Let's go to the final results. With these materials we have in mind, these are the cooling here and the heating and the cooling temperatures values in a specific case, that is with a current intensity of 300 milliamperes for our selected meeting materials. And you have the dotted curve, which is the results, the numerical results given without introducing in the general equation also the phase transformation latent heat, and the blue one, which is those in which the effects of latent heat are introduced in the energy balance approach. As you can see, this introduction of the latent energy, generally speaking, does not modify too much the results which are obtained. If we want to be a little bit more precise, we can say that they are essentially neglectable during the heating phase. You can see that the two curves are essentially the same. There is some differences during the cooling phase. So if you want to be a little bit more precise, just use the effects of latent heat of transformation when you are going to model the cooling phase, that is the decrease of temperature, both in case of free convection or in case of forced convection. But at an overall approach, in this case, if we neglect in both cases heating and cooling the effect of latent heat of transformation, we are not making a very high errors. This is the, let me say, the meaning of these results. Last part, which is requested to us, is to have if you remember the mechanical model. I mean, we need to put in relation the stresses, in this case the force, which is given back by our materials when it is modifying its shape and size due to the activation of the shape memory behavior. These are equations which can be used for helical springs. I've given to you, let me say, something which is not usual. I mean, something which includes also, this second case, the possibility to have some plastic region. Otherwise, the standard in elastic region behavior is what is given by this force and this equation, where you have here delta, which is essentially the deflection, that is the displacement of the materials, that is of the spring, due to the change in shape for the activation of the shape memory behavior. And so with this final step, using obviously the correct values of the materials, for example, in terms of shear modulus, we are able to define diagrams for which force, that is stress, if you want, is plotted against the deflection of the springs itself. And so we can know, according to the expected deflections due to the shape memory behavior, which is the force which is made available to us in order to move something, in order to move an object. So in order to have the actuation of a movement. And then you can make all the simulation that you want. You can see, for example, what is going to happen if the temperatures are going to be varied to different extent, if you have a different number of coils of your helical springs, etc., etc. And so all the elements which can be useful and which are necessary to design this spring, which is based on shape memory behavior. Having said that, let me add some interesting things related to another class of materials, which belongs again to the smart material classes. We told at the beginning of this discussion last time that smart materials are a broad class of materials. One of these are the shape memory alloys, but not only the smart materials are shape memory alloys, because we have piezoelectric materials, electrostatic materials, magnetostatic materials, etc., etc. Among these, the materials that I want to discuss a little bit with you, which can overcome the frequency limitation in terms of behavior of shape memory alloys, that is, this class of materials are those we can actuate also fast movements, which is not possible for shape memory alloys like nitro, are the piezoelectric materials. So here you have a description of a different class, but let's go directly to the piezoelectric materials. What are these piezoelectric materials? Well, piezoelectric materials are essentially materials which are able to develop, to give to us voltage when we apply, when we are going to applicate a stress, or because they have a reversible behavior, they can deform that is, they can develop a strain when they are subjected to an electric field. This is piezoelectricity. Well, let me say, I will be back. Here, okay. Let's use this one. Okay. The most common piezo materials are belonging to the class of ceramic materials. And one very known is the so-called PZT materials, which is lead zirconate titanate, this one, okay? Now, let's make a small discussion. This is a ceramic material. So if we are thinking to use these kind of materials when there are, for example, engineering, let me say, applied loads, we are a little bit worried because we know that ceramic materials, generally speaking, and also piezo ceramic materials, they are brittle. So they have a very low value of fracture toughness, which is around some units of megapascal per square meter, which does not allow to the materials itself to show a good tensile strength due to the fact that defects are always existing and due to the fact that defects can be easily propagated when we have a tensile stress field around the defects in brittle materials. So for some of our application, it will be beneficial if not only ceramic materials belongs to the piezo class, and we will see that there are some polymeric, essentially a couple, essentially one, materials which are able to show the piezo effect. And this is, let me say, very interesting for us. Why it is very interesting? Because obviously, if we are talking about polymeric materials, we do not have problems of brittle behavior as well as we have in the class of ceramic materials. Secondary, because you know that a lot nowadays of structural components for the aerospace fields, not talking obviously about high temperature application, but talking about room temperature as a reference applications, are made of composite materials based on a polymeric matrix. So if we have some polymers which can show a piezo effect, one thing that could come in mind, not the only one, but one, is to place this polymer as a part of the matrix of a polymeric composite-based materials in order to have, for example, a sort of health monitoring of the component itself, because that polymer materials, when stressed, if it has a piezo behavior, can give back a voltage. And if we are able, and we are able to measure the voltage, we could say how much is the applied stress. And so the interest in more advanced application for the aerospace on piezoelectricity is related not to the classical, which is very important, piezo effect, which can be given by ceramic piezoelectric materials, but by the possibility, is given by the possibility to use, and we will see some example, piezo materials which belongs to the class of polymeric materials. Having said that, if we come a little bit back on the class of ceramic piezo, let me say that this piezo effect, without being too complicated in this discussion, is related to the fact that these materials can be conditioned dipole orientation inside the grains, so they are polycrystalline. In a classical configuration, dipole orientation inside grains is random. So there is no resulting polarization vector. The ceramic materials which can exhibit a piezo behavior can be conditioned so that all the dipoles are equi-oriented and thus resulting in a polarization vector, which is the reason because the piezo effect can appear. And this is a technological process which is going to work, for example, with lead zirconate titanate, but which is not going to work, for example, with alumina. So the number of piezo ceramic is not so high. And when we are in this configuration, so we do have a residual polarization vector due to equiaxed orientation of electrical dipole inside the materials grain, talking for the ceramic base, we can have this effect. In the case in which we apply a voltage, that is an electric field, for example, which has the same direction of the polarization residual vector. In this case, we can have a resulting strain, an axial strain. In the case in which we apply, like in this case, an electric field which is perpendicular, that is orthogonal to the residual polarization vector, we do have again a strain, but this is not a normal strain, this is a tangential strain. That is something which is a transverse strain. And we usually refer to this case, the case in which we do have axial strain, in order to use the piezo effect in piezo materials. And there are some also, if you want, complicated modeling, but there are also very simple approach which can give to us the possibility to calculate at a glance what is going to happen. And one simple approach is those which is based on coefficients which are known for the materials which show this effect. And essentially, these coefficients, so that this is a monodimensional approach, are two. One is called D coefficient, the other one is called G coefficient. This G is essentially more used, which, as you see, in a linear array, the unit of measurements are millivolt per Newton, are able to tell to us, for example, how many millivolt are generated when we apply a certain value of Newton, okay? And for the direct piezoelectric effect, And so this can be used, for example, for making some calculations. Here you have the PZT, you see here, which is the materials we have mentioned before. Another one is barium titanate. Essentially are these two, the ceramic piezo materials with PZT, which is the most efficient, generally speaking. And when we know, but we know that because they can be found in literature, these values of coefficient, we can, for example, make, as you said, some calculation in order to understand how these materials behave and which is the piezo effect. Here you have a simple example related to the design of a spark ignitor. These are real values, okay? And so, for example, let's take a disc, very thin disc, small disc, sorry, with 5 millimeters in diameter and 2 centimeters, that is 20 millimeters innate, okay, made by PZT with his G coefficient, which is those given in the previous table. And assume that this small disc, on this small disc is applied a force in a compressive way. So we are not talking about tensile, we are usually talking, for the reason we had told before, about the application of compressive force, which is 10,000 Newton. So the question is, how high is the voltage which is generated, for example? Well, giving the definition of G, which is this one, so it is the ratio between the electrical field and the stress. This is the definition of the G coefficient. We need to calculate, in this case, the electrical field. Then if we know the electrical field, we can calculate the voltage, the difference in voltage. So let's have a calculation very easy of the stress. It's the force divided by the area, okay? The stress, so it's calculated like it is indicated here. If we multiply this value of stress for the G coefficient, we then get as final value of this multiplication 1.782 10^5 volts per meter. And this is the value of E. Then if we multiply the value of the electrical field for the thickness, 8, of the disc, that is 20 millimeter, we are able to calculate the voltage. And you see here the figures. It's more than 3,000 volts, which is not so low, okay? So this piezo effect can be an effect very, very, let me say, significant in this way. Now, this piezo effect for the ceramic materials, generally speaking, has to take account some limitation, and this must be remembered in order to have a more complete panorama. First of all, if we apply a voltage on an electric field which is too high, then we can cause a depolarization effect. And this is said that we do have for each piezo material, let me say, a maximum applied electric field which is able not to cause the electrical breakdown, because if we dipole if we start the depolarization effect, then the piezo behavior is lost. And so this is the first limitation. The second limitation is related to the fact that there is a maximum temperature which is around 350 Celsius, above which, again, depolarization occurs. So this is called the Curie temperature, which is proper of the piezo materials itself. It's not a unique value. Each piezo has its own value, but around 300, 350 Celsius. And so for temperature which are higher than the Curie temperature, we cannot more rely on the piezo effect because depolarization has happened. And then it depends on the piezo materials as well as on the, for example, the entity of the applied stress. Usually we do have a linear behavior, like we have implicitly said here. You see, this is a linear behavior. But we can have also non-linear behavior, sometimes some hysteresis. This must be taken into account when, for example, we want to use these kind of materials as sensors. Impact sensors are made by piezo. What is going to happen when you have an impact? You have an impulsive load applied, but you have a stress. So see, if this impulsive load is applied on a piezo materials, the piezo materials, which has the property to have a very fast response, it can work well for hundreds of hertz, gives back a voltage. If we measure the voltage and we have a graduation scale, we can calculate which was the load transferred by the impact, the impulsive load. So this is a sensor which is made by piezo materials. Apart from, let me say, very simple application which are not related to aerospace application, for example, the use of piezo igniter in lighter for smoking people, or piezo igniter in your kitchen, okay, where you light on gas, methane. That one are based on piezo effect of ceramic materials. So PVDF, it's a quite complicated name. PVDF is the real up-to-date polymer materials which is able to show a significant piezo effect. So we do have, and here you have the constant of PVDF, we do have the possibility to rely on this behavior also with one polymeric base materials. Here you have an extensive, let me say, representation of possibility to have piezo effect also in other polymeric matrix, and in this column the value of the constant are specified. But to summarize, so this is just for you to summarize, the PVDF is the most important. And what we can do with this, for example, we could think to use this instead of shape memory alloys, due to the fact we said already that the shape memory alloys in principle can, but really are not able to follow fast movement, but piezo instead yes, because the basic phenomena is another. We could think to use this for vibration control. For example, if you have a beam, okay, which is vibrating, and you put, and this is not very difficult, a PZT patch or a polymeric patch on the beam, and if you make the configuration in the sense that the patch follows the vibrations of the beams, the deformation, the deflection as you want, then what are you doing in this? You are going to deform the piezo materials. When the piezo is deformed, it gives back a voltage. So if we close an electric circuit with a resistance, for example, or if you want with a resistor and an inductor, some current intensity is going to flow in the electric circuit. And what is going to happen? What we have already seen before for the spring example, we have power loss, joule power loss. But joule power loss means energy loss. And energy loss in this case means that we are going to reduce the amplitude of the vibrations. And this is, let me say, the active way to contrast, or in some cases to suppress vibration. But you can have also an indirect approach. That is, you can force deformation of the piezo materials by applying externally a voltage to the piezo materials. And if you force the formation of piezo materials in a counter phase, phase opposition with respect to the vibration, so you are essentially increasing the inertia moment of the ball structure, and so you have amplitude of the vibration which are going to decrease with time. So you can have direct or indirect vibration suppression or vibration control. Or you could have, for example, let's go here to the possibility to modify profiles of wings, okay, by using, in this case, polymer, essentially polymer-based piezo materials, which can assume specified forms with respect to the fact that current intensity is forced to flow inside the piezo itself. That is, we are going to apply a difference in potential, and so we have a strain. If this system is not free to deform as it wants, but is fixed in some points, we can have effects like those reported here in this picture, in order to have, for example, an active flow control. And so controlling the interaction between the wings and the fluid, generally speaking. Or, as I told to you, you can also think, in the case you have a composite, polymeric-based composite materials, to put some part of the matrix, in some part of the polymeric matrix, the piezo polymer, in order to have a sort of embedded sensor of strain. Again, you need to instrument, but this is not very complicated, the sensor, the part in which the piezo polymer is inserted, in order to catch, in order to measure the voltage, and so having the results of the applied stress, which makes able the deformation, that is the strain, to exist on the piezo materials, which is responsible of the voltage which is generated. When you have plastic materials, like in this case, even though it has a piezo effect, one question would be, well, but in order to measure a voltage difference, or in order to impose a voltage difference, we need to have a sort of metallic conductors. So just to explain very easily, if we have wires, we have to connect to the piezo polymer. Well, how can we do this joint? Well, don't worry, that's not very difficult, because you should remember that we can have available for engineering applications surface engineering technologies which allow to us to make coatings also on non-metallic materials, also on polymeric materials. So you can make a metallic coating, thin coating, for example, by using physical vapor deposition or chemical vapor deposition technologies, surface engineering technologies. And so you have a sort of condenser. So the inner part is the piezo. The very thin metallic sheet are put by using a vapor deposition method, and then you can joint your wires, metallic wires, directly to the metallic part, which is strictly in contact with the piezo, thus having the electrical contacts that you need, for example, also to make this one, okay? And thus using this class of materials for these purposes. Okay, I think that for today we can finish our lecture. We have closed this argument, and on next Friday we will start another one. Okay, sorry, I'm a little bit delayed, but okay, it's fine. You have any question?
Professore,
Eccoci.
e sempre quando ha fatto l'esempio, diciamo, dell'attuatore,
Sì.
ma come possiamo passare, diciamo, cioè noi fondamentalmente abbiamo ottenuto una equazione della dinamica che è relativa